generosity. Okay, so I don't have a lot of experience with millet, a little bit with sorghum. I have experience with many other crops. And today I will share with you some information about lysimeters. I don't think it really matters which crop we are talking about. Lysimeter is a concept, and this concept is something that I want to share with you today. So with this lysimeter, what we want to do is to look at plants while they are growing in experiments or in field conditions. And we want to understand and to estimate what's going on with the water. Where is the water? Where is the water molecules? Where are they? And also with the water today, it's not only water that we are giving to the plants, it's also chemicals. It can be fertilizers. It can be other solutes that are not good to the plants, like chloride or sodium or other. We have a lot of salinity in Israel. We are irrigating with saline water. And other agrochemicals that we are introducing into our agricultural crops, like herbicides or pesticides. So today what I will do, I will review the lysimeters. Lysimeters are those containers that we are growing plants into those containers. And I will review some of the limitations, some of the things that you need to take into account when you are growing with the lysimeters. I will give some case studies, different case studies, the conditions and the know-how that we gained through the last, I think, even 20 years of using lysimeters. And then I will conclude. And finally, I will show you some interesting summer course that we have in our institute that I think the connection between our institute was initiated in this summer course. Okay, so by the way, these pictures was taken 1 week ago with the bell pepper experiments in a greenhouse in a very hot place in Israel when we grow vegetables. And the farmers in this area are using this information from the lysimeters to irrigate and fertilize their crop. Okay, so my objective in my research is to understand water flow and solute transport in the soil plant atmosphere continuum. Water is coming from irrigation or from rainfall sometimes. Sometimes we don't have a lot of rainfall here. Our annual precipitation here in my campus is 92 millimeters. This is the average precipitation, so it's not too much. We are irrigating. We must irrigate because if we are not irrigating, we will have stress, and therefore we must supply water. And with the water, always, as I mentioned before, we have agrochemicals, fertilizers, and other agrochemicals. And we want to increase agricultural productivity. It's not only the yield that we want to increase, it's also the quality of the produce, sometimes size, sometimes the composition and taste, aroma, and it depends on the crop. And while doing so, we want to maintain the environmental sustainability, because with the agriculture, we can make pollution to deep wet ozone or deep soils, because some of the agrochemicals will drain below the root zone. So we have a deep percolation. And with the lysimeters, we want to investigate those processes. Those processes are really, really important. With lysimeters, we cannot investigate all the processes that are happening or all the fluxes that are happening in the agricultural root zone, but the majority of them we can investigate. So what is lysimeter? Lysimeter, the word lysis is derived from a Greek word, lysis. It's meaning dissolution or separation, and the metron is to measure. So lysimeter is to measure the separation. What is the separation? First is the water balance, the water balance component separation. So I write a small equation here with the water balance of the main fluxes in the root zone, which ET is the evapotranspiration, evaporation from the soil, and evaporation from the plant. We call it transpiration. It's equal to the irrigation, the amount of water that we supply. It can be also precipitation, minus the drainage. The drainage is that the fluxes that are coming below the root zone, and the change in the mass of water inside the soil. We have a change in water content inside the soil. So water content can increase or decrease inside the soil. So if we have this container, and inside this container, you can see a date palm tree. Date palms are commonly grown in Israel. And something that we want to understand, really want to understand, what is the transpiration of the plant? Because when we will not give enough water, plant will close the stomata, and transpiration will be decreased. And when we are giving too much water also, plant will have a stress, and transpiration will decrease. So we need the optimal condition. So the question is, what should be the irrigation? In the same time that we have transpiration, we have evaporation from the soil. We can minimize it by putting mulch on top of the surface. And often that's what we are doing with lysimeters. We are putting mulch. Also in agricultural activities, the farmers are putting mulch on top of the soil to minimize evaporation, because it's not productive flux. The drainage is coming below the container, and we can collect it. We can collect it and analyze the mass of the drainage. We can also analyze the composition of the drainage. Below the container, we have a scale that measures continuously the change in storage, the water content of the entire container. And the change of this water content is delta S. So if we are doing the analysis correctly, and if we are minimizing evaporation by knowing irrigation, changing storage, and drainage, we can calculate the transpiration. Often we say that it's just an estimation, because sometimes we have other processes that are happening in this mass balance, is also the growth of the plant. So if we are looking at a very short time differences, the growth is really minimum compared to the water fluxes. But if we are looking at very large times, the growth obviously is something important. And we can even analyze the growth of the plant with lysimeters. Now, after we talked about water balance, let's talk about solute balance. So the uptake of any solute is equal to the irrigation multiplied by the concentration of the solute. It can be any solute. It can be chloride or sodium or nitrogen, or any solute that is coming with our irrigation water. And we can do this balance separately to any solute. But let's first talk about tracer, like chloride, that is not changing in the soil and not absorbing, and it can only accumulate and go below as drainage. So the drainage multiplied by the concentration of the drainage, and the storage of water is also always multiplied by the concentration, and then we can do the balance and see where is the solute, because we are interested in the solutes as well. The uptake is really important. We want to understand how much the plant uptake, because we can manipulate always the concentration of the irrigation. In many fertilizers, we can manipulate not only the concentration, but also the species. So if we are bringing nitrate or ammonium into the game, it's really important, and we want to understand what should be or how much is the uptake, because we can change and schedule differently the irrigation and the fertilization regime. And we want obviously to see the effect on the crop, to see the yield and the root distribution and other things that in container it's really easy to do compared to field conditions. Also in field conditions, we almost never have this drainage. And the drainage that coming below the lysimeter is something that is like a gift that we can analyze and see what's going on inside, because under field condition, it's really hard to get this value. So what are the objectives of lysimeters? I give here 5 different objectives, and I will give, for each one of them, I will give a case study that illustrate this objective. So first is to estimate evapotranspiration. I think this is the main thing that people are using lysimeters in the world. If, as I mentioned before, if you are putting mulch on top of the surface, it's just the transpiration. If we are not putting mulch, it's this evaporation and transpiration together. Also under field conditions, many farmers are not putting a mulch on top of the surface, and they are wasting water, by the way. And yeah, lysimeters can help us to estimate this very important term, evapotranspiration. Most of the water in our conditions are going to this evapotranspiration. So the irrigation is converted later to an evapotranspiration. Second thing that lysimeters are doing are estimating solute uptake. We need to understand solute uptake because we want to know what should be the fertilization regime. We can calibrate soil, plant, and atmosphere models. We are using models for water flow and solute transport in the soil. And to calibrate those models, those mechanistic models, we need data, and this data can come from lysimeters because we can control the fluxes in lysimeters, and we can really accurately measure those fluxes. Sensors, we are using many sensors in agriculture today, and those sensors, before using them outside in the field, we want to see if they are doing correctly. So we can use lysimeters because we are pretty sure what is the transpiration of the plant, and we can compare the sensor measurement with the results of the lysimeters. And finally, agriculture can be a really big player in pollution of deep wet ozone and groundwater, and we want to minimize the pollution, obviously, because we want to have a sustainable production, and the solute load below the root zone is really important, and we want to analyze it, and I'll show you some example. Okay, so lysimeters. We can see here pictures of lysimeters with different crop. It can be date palm growing on huge, massive lysimeters. We can see here sweet basil grown on relatively big lysimeters in field conditions. So you see that the crop that is growing inside the lysimeters is almost similar to the crop that is growing in the row of the farmer. And we can compare the yield and the quality. But in the lysimeters, we can also estimate the evapotranspiration. We can see here a pomegranate with a huge experiment that I did about 10 years ago with different salinities. It can be drainage lysimeter that I will explain later. And this is a nice device that I have it in my greenhouse. This is a carousel device that will give me continuously and automatically the water and the solute balances. So this carousel is rotating continuously. And I think it's a sorghum here grown in this greenhouse. And this experiment was a salinity experiment. So we had 5 different treatments with the repetitions, and we analyzed the transpiration while the plant was growing. So everything is done automatically. The irrigation and the drainage collection is done automatically using a robot. Okay, so let's talk about difficulties. Size, as you see, is really important. You can see here in the previous example, different size, different container size. For date palm, we use the huge container. For cassava small plants, we used about 60 liters. And after 1 season, the container was not good enough to grow the cassava. So we needed to change or to finish the experiment. In these date palms, you see big, relatively big trees growing on lysimeters. This experiment was done to investigate different irrigation regime with high and low and medium irrigation compared to what the farmer is doing. And also we use it to calibrate sensors, subflow sensors. And we also did some electrical resistivity tomography measurements when you are implementing a current into the stem and measuring the voltage difference just to see the distribution of the electrical resistivity from a tomography. Yes, so you're doing it from outside and you want to see what is inside in the stem without being inside. So you have a lot of cables and a lot of machines that are measuring. But if you see the lysimeters and the roots, after 3 seasons, the containers was too small. And the container size is really important. Roots are growing there, and you need to supply irrigation water to this volume. And if the volume is too small, the roots know, and they try to break it. And that's what happened. Even if we put metal and we weld it, and we put many things to prevent the expansion of the container, it broke. And if you have a leakage from this broken lysimeter, it's not good because you are underestimating the evapotranspiration. So this is a bad process, and you don't want that it will happen. You need to adjust the lysimeter size to the crop. So date palm, after 3 years, you need to or transplant them to another bigger container, or you need to finish the experiment and investigate the root zone or whatever you want to do. But you cannot continue like this because it's kind of a stress to the plant. Root restriction is big stress for the plant, and the plant will behave differently. So size is really important. In the other way, you don't want that it will be too big. Yes, because too big is really expensive. Those lysimeters need scales, and the bigger the scales range, the more expensive. The bigger the container, the more work you need to do to fill it up, etc. And so price is really an issue. So you need a optimum between a big size that is very expensive and a small size that it will be stressed to the plant. The lower boundary condition is really an issue. And if water want to escape in the lower boundary of the lysimeter, basically the pressure there is 0. So the water is absorbed to the particles, and the water cannot escape until there is a slightly positive pressure. If there is a slightly positive pressure in the lower part of the lysimeter, it means that in the higher than this, it's still saturated. The water content is saturated, and it's not so good for plants, because when the water content is saturated, we don't have oxygen, and the plants suffer from lack of oxygen, and the uptake will change, etc. So what we want to do is to drain the lysimeter and to have similar conditions like in the field when we have a deep drainage. So one approach to do it is to put suction, to put a vacuum pump, and you need to, in the lower part of the container, to put a porous material to enable the vacuum to become pressure head in the soil. However, this is relatively expensive, and if you are doing it on large scale, you need many pumps, and the porous material is expensive, etc. One alternative is to use rock wool. Rock wool is a porous material that you put in walls for insulation. So it's a material that we can buy in the market. And now this rock wool is kind of extending the hydraulic of this container. And basically the very wet conditions now are just in the lower part of this rock wool. And here, in the interface between the rock wool and the soil, there is a negative pressure head. And it means that the water content is not saturated, and you are becoming closer and closer to fill capacity in hydrostatic conditions. So, and then the question, what should be the length of this extension of this rock wool? Alon Ben Gal, a colleague of mine, did many experiments, and from very short to very long extension, you can see that the volume that is generated below the container is increasing with the increasing of the length of this extension. Obviously, more than 60 centimeters, it's quite hard to do because you need a space below the lysimeter. And here in these conditions, I think 40 centimeters would be enough. Also, you can see that the drainage, after the irrigation, it takes some time to generate the drainage. It takes about 15 hours that you see that the soil become into hydrostatic condition when drainage almost stopped. So the lower boundary condition is really important. And if you will just put a container without anything, all the water that you irrigated will stay in the container and you will not have drainage. And if you have a sandy soil, it's not so bad because you still have enough air inside and the water is not held in the capillaries in strong forces. But if you have a clay soil, you have really a problem, and then you must have this extension. Even in loamy soils, you must have those extensions. Otherwise, you will have a very wet conditions. So size and the lower boundary conditions are really important in lysimeters, and you need, while designing the lysimeters, you need to take them into account. Now, we have a lysimeter, we designed a size, we designed the extension. Now we want to put soil in the lysimeter. One way that I'm usually doing is backfilling the lysimeter with soil. And I'm trying to have a constant bulk density because I want that the same soil that I had in the field will be also in the lysimeter. It's hard work, but it's not too hard compared to the undisturbed soil that you can see in this picture when they are pushing the cylinder into the soil, and then taking this cylinder to the place when the lysimeter going to be. And finally, the lysimeter is really part of the surrounding soil. So this is to have exactly similar conditions, exactly similar layers, exactly similar microorganism, organic matter, whatever that was in the soil in the field. So of course, depends on your question and what is your hypothesis for your research and what is the objectives. You need to choose between taking undisturbed soil, which is a lot of effort, but eventually you will come to the same similar conditions like in the field, or backfilling it, just taking soil from the outside and trying to have same layers, same bile density, but still it's undisturbed. Sorry, still it's disturbed soil. So this is a big question mark what you want to do. And of course, it's a budget issue because undisturbed soil, you need to have a heavy machinery, but finally you get similar conditions. Okay, so you have lysimeters, and you want to know what is the difference between the lysimeters and the field. When I'm growing plants in the lysimeters, are those plants are similar? Are they giving the same yield, the same transpiration, the same behavior like in the neighboring plant in the field? So this is something that we wanted to check in one of our experiments. I had a PhD student that dealt with this. And what we did is we used several sizes of lysimeters. And those lysimeters were very simple lysimeters because we wanted to give farmers this approach. And while doing so, we said, okay, let's take the scale out. If we're using saline water, in long-term processes with saline water, we have relatively homogeneous distribution of water in the soil. So therefore, you maybe don't need the scale because the change in storage in long-term is almost equal to 0. But we wanted to check what should be the dimension of this container. So we took 150 liters, 300 liters, 1200 liters, etc. Containers. And we collected the drainage in a container. And into this container, we had this pipe that we can, and you can see it here in the field. And from this pipe, we collected this water with a vacuum pump just to see the water and solute balance. So after doing this nice experiment, we can see the yield of the bell pepper along the time. Bell pepper is grown in Israel in this region in the autumn and winter. And we are starting to receive yield. And we are collecting yield in the 10 different times. And in the end of the season, after half a year of after starting the experiment, you can see the field plots in black. We have about 11 kilogram of bell peppers per meter square. Of course, everything is irrigated with drip irrigation. We're putting the fertilizers into the irrigation water, so we are doing drip fertigation. In this experiment, we had also weighing lysimeters, big weighing lysimeters, and you see that the weighing lysimeters did not produce the similar yield as the field plot. One of the reasons that we believe that it didn't give because in the pre-season, we need to disinfect the soil, and we are putting plastic mulch, transparent plastic mulch on top of the soil. And in these containers, the plastic mulch was not properly done. And we think that still we had some nematodes there, and the yield was reduced compared to the field plots. In some of the lysimeters, you can see that when we have 1 meter square already with 4 plants, it gave us a very good representation of the field. But if the lysimeters are too small, you have only 2 plants, it's not giving a good representation, and the average is too low. And if the lysimeter depths, you see we had 0.6 and 0.3. Also with 0.3, usually we are not getting enough space for roots to develop, and we have too wet conditions, and the yield is reduced. So you need to take all those into account while designing lysimeter. How many plants you're going to put inside, what should be the dimension of the lysimeter, what should be the lower boundary condition, etc. Another thing that is important was important in this experiment, we are using weighing with scales. Again, scale is expensive. Scale, you need to buy the scale, to calibrate the scale, and to do from time to time checking of if the scale is still working and can give you a good calibration. Or if it's a drainage lysimeter, when you're checking only the incoming water, the irrigation water, and the drainage water. And we check the evapotranspiration with both approaches, with the big lysimeters on scales or the big lysimeters not on scales. And we got relatively similar values. Just to remember that we are in a greenhouse in the winter, therefore the evapotranspiration is not too high in the greenhouse. In the end of the season, when we are approaching the spring, we see a dramatic increase of the evapotranspiration. But in the weighing lysimeters, because the plants were a little bit smaller, we could not see it. So weighing or non-weighing is a matter of a question. Of course, weighing, you add another component of scale, which is expensive, and you need to maintain and calibrate. Drainage lysimeter are really, really simple, and even farmers understand really how to work with them. But you cannot do everything with drainage lysimeters. If you're looking at daily evapotranspiration, yes, but hourly, of course, you cannot do with drainage lysimeters. This is an example of this rotating lysimeter for my water use efficiency studies. This is a container. I have 24 containers. All of them are located on load cells. So we have a continuous measurement of the mass balance. You see the drainage is going into another container. Here is then another container. So we want to collect the drainage. And from time to time, we lower with the automatic piston, we lower this handle, and we're collecting the drainage with this blue container, and we are measuring the drainage mass and the electrical conductivity. This is done automatically. We have also a camera here that takes pictures while the plant is going, so we want to see the development of the plant. And also the irrigation is done automatically using a robot that's preparing the water and dosing the water into those intermediate container, and from there, with drip irrigation, it will irrigate the plant. So everything is done automatically. All this information is collected into a computer and then transported into the cloud immediately. And I can sit in my office, see all the data, and I'm really, really happy that everything is working. This carousel is quite expensive, but it's generating a lot of data, and it's quite a powerful tool to conduct research. I'll give you a few examples now of estimating evapotranspiration with these day palm trees grown in a hyper-arid condition. In this area, we almost don't have rain, maybe 20 millimeters per year, so we must irrigate. We are irrigating approximately 2,000 millimeters per year. We need to bring this water, and the big question there is how much to irrigate, because if we don't irrigate enough, the crop will be small. And the fruit will be small, and every fruit of the date palm is approximately 1 shekel, which is our currency. It's approximately $0.25 fruit. So in order to generate 1 fruit, you need to irrigate 40 liters. 40 liters per 1 fruit. 2 fruits is 80 liters, is approximately 1 shower. So you need to choose between making 1 shower or to eat 1 fruit. And yeah, we are looking at the daily transpiration of this plant in kilogram per hour. Those are small plants. Those are not big plants. And we have a 3 irrigation regime with low, normal, and high. And as you can see, during the nighttime, the transpiration is almost 0. The sun is shining and the stomata will be open, and immediately water will evaporate from the stomata. This is the transpiration process. And you see this increase in transpiration until the middle of the day. And then the climatic conditions are changing in this region. It's cooler, and the radiation is decreasing, and the stomata are getting closed, and the transpiration is decreasing. You can also see that there is a difference between the different regime. While the low irrigation transpiration was in the middle of the day was 5 kilograms per hour, in the higher irrigation, because it has a much more availability of water in the root zone and the stomata are open, the evapotranspiration was 7 liters per hour. So this is something that you can do with lysimeters with scales. You can estimate the hourly transpiration. And this is very powerful tool because you can distinguish between different varieties, different treatments, different whatever you want, different soils, whatever you want to investigate. Very powerful tool. Here is an example of peanuts grown in field conditions. Those are huge lysimeters. This is 2 meters by 1 meter, and the depth is 1 meter. So it's a 2 cubic meter located constantly on a scale in the field, measuring the transpiration of the plant. Here it's evapotranspiration. Again, we have evaporation from the soil. And this is done because we want to understand the evapotranspiration, how it's behaving compared to the potential evapotranspiration that is measured with the meteorological station. And if we have the potential and the actual, we can estimate the crop factor. Crop factor is a factor that is dependent on the soil and the plant. The plant is obviously starting very, very small, and then it's growing and growing and growing. And in the end of the season, we have a fully covered plant, and then the plant is aging, and then we harvest the peanuts. If we have this evapotranspiration, we can calculate the crop factor, and then we can transfer to the farmer, because in the next season, they will not have the actual evapotranspiration, but they will have the potential. And since we already have the crop factor, they can multiply the crop factor with the potential and get the actual evapotranspiration without having a lysimeter. So this is for irrigation purposes. In the beginning of the season, we have a small plant, but we are starting in the summer, and the plant is growing, but we are going towards the autumn, and here the plant is bigger and bigger, but we are going into the winter, and the evapotranspiration is decreasing and decreasing, and we want to respond with our irrigation. We cannot irrigate the same. We need to adjust the irrigation relative to the evapotranspiration to maintain a favorable condition in the soil. we don't want too less or too much water in the soil. A third example is about solute uptake. Here I give an example of nitrate and the chlorides. In this drainage lysimeters that I showed you, this is Yael, my former PhD student, and this is the lysimeter that we embedded later in the soil. So we are growing the plant inside the container, and you can see the blue line here is exactly this phase of this lysimeter. So we have the irrigation amount in gram per meter square. 0.5 kilo per meter square per season was irrigated, came with the irrigation water. And we can see the drainage in different sizes of lysimeter. So if we have the irrigation and we have the drainage, the difference between them is what is inside the soil. This is or the uptake into the plant, or what is in the soil, or in the case of nitrogen, it can be also evaporated in the nitrogen. The difference is really important because we can do this difference not only in a seasonal base. If we have a relatively small volume and the soil is not absorbing too much, if you use perlite or other soils, you can do it even on a daily basis. Here is an example of chloride irrigation with saline water contain chlorides 700 grams per meter square. Imagine almost 1 kilogram of chloride, a bucket of 1 kilogram per 1 meter square is coming with the irrigation. Most of this chloride is in the drainage. It's not in the soil, it's going to the drainage. And this is something that is polluting our groundwater with chlorides, because chloride is not so good to drink later on for people. So when we are using saline water, you need to think about it, and you can estimate how much is going into the plant. In terms of nitrogen, is quite a lot. This is the difference between the irrigation and the drainage. In terms of chlorides, is very minimal. A fourth example that I want to show you is how we are calibrating soil plant atmosphere models. We are using models to simulate the condition in the root zone. One of the models that we are using is Hydrus. It can be Hydrus 1D, 2D, or 3D. Hydrus is a family of models that simulate the conditions inside the soil, the water flow, and salt in the soil, how the salt is moved from one location to another, and how the water is moved from one location to another, how the water is uptaken by the plants. And the reason that we are using models is because this experiment that we are doing is in one location, in one condition, in one soil, but we want to go outside to give some recommendation to the farmer, and the farmer might have a different conditions, different atmospheric conditions, different soil properties, sometimes even different plants. And then we want to give a recommendation. So we need something, a model that transfer the information that we gain in the lysimeter to the outside real world, because the lysimeter is not the real world. The real world is outside there in the field. So what we are doing is taking the points. The points are measured data. Here it's irrigation, the measured fluxes of irrigation, and the measured fluxes of drainage, and the measured fluxes of transpiration in this case. And we want to estimate with the model, and the line is a model, yes, is not data. It's just we are comparing always to the data. And once we have a good comparison, we said that we have a calibrated model. And once we have a calibrated model, we want to test it. Is the model is good predictor for the environment that we are simulating? And if yes, we can use the model as an experimental tool. we can ask question, because in experiment, how many treatments we can do? 4 treatments, 6 treatments. In a model, we can do as many treatments as we want. We can do sensitivity analysis. We can change some of the parameters and see what is the response of the model. And here we could estimate the emission of nitrogen or the drainage below the root zone. Yeah, so with this accurate information that is coming from a lysimeter, because we have a controlled volume and we are measuring the fluxes quite accurately, we can understand and estimate fluxes that we don't measure, and the model is helping us to transfer this knowledge to another location. Another example is sensors. Sensors are something that we want to use in agricultural conditions, because they can tell us what's going on, what is the real conditions. Because with the farms, we cannot put lysimeters everywhere. It's very expensive and tedious. So we want to use sensors or in the soil or in the plant. Here I give you example of a plant sensor. This is a sap flow sensor that measuring the transpiration stream in the stem of date palm. So we have those electrodes that we are pushing into the stem, and those sensors are emitting a little bit of heat into the stem, and this heat is transported with the transpiration stream. So during the nighttime, there is no transpiration and there is no in the stem. Therefore, the heat is generated and is measured with thermocouples, and we can see increasing temperature. And during the daytime, the transpiration stream is taking the heat away. The heat is dissipated away from the sensor, so we can measure it. So what we did is we took sensors and we put them also in the lysimeters, and we could compare between the heat dissipation sensors and the weighing lysimeter, and we have most of the time good comparison, not during some hour of the day. And the reason is that you're actually measuring 2 different processes. The lysimeter is measuring the water flow outside of this volume of plant soil, and the subflow is measuring the water fluxes inside this volume. Sometimes they are not the same, because during the daytime there is some storage of this trunk, and there is a reduction in the water amount in this container. The trunk is filled with a lot of water. But anyway, all in all, we can do this comparison between the lysimeter and the sensor, and we could later on take the sensor into locations without lysimeter and estimate how many gram per meter square per second we are losing from the trees. And this is a really powerful tool. Last example for today is salt or solute load to deep soils. Here I'm giving an example of chloride. Chloride that is coming with our irrigation water. This groundwater is really saline. So one way is to reduce the salinity is to desalinate the water. So in Israel now, we are desalinating water and we are using it for use in our houses. But some of the water will flow to agriculture. And yes, the price is decreased. And now it's not too expensive to desalinate water, even to irrigate with the high value crop. Now the question is, because you desalinate the water, you take out all the salts out. The question is how to bring some calcium and magnesium and sulfate in the water. So one approach of the farmers is to blend the water. So we have an experiment with groundwater, which was saline, desalinated water with very low quantities of chloride and blended water with a very, very low, salinity, but still not lower as the desalinated water. So if you are measuring the concentration of chloride in the leachate, you can see that in the beginning of the season is really low, but there is a difference between the desalinated water, blended water, and the groundwater. When the plants are growing, you have more and more chloride in the drainage water. And if you have the amount and you have the concentration, you can calculate the drainage and see how much chloride is in the drainage, and this chloride is polluting the aquifer. I'm almost in the end. Here you see different crops. Bell pepper, sweet basil, tomato grown in the same lysimeter. So these containers are good for several crops, season after season. You can grow there, but you need to take into account that you need to do the same plowing or the same things, the manipulation that you do in the field. You need to do also in the lysimeter. Otherwise, you will not have the same crop. The roots will behave differently, the crop will behave differently. So you need to try to maintain the same processes that you do outside, also inside the lysimeter. And if you do so, you have a very similar conditions, and also the evapotranspiration and the drainage and the quality of the drainage. And this is really powerful tools to help our research. So my conclusions. Lysimeters are great research tool. You have the drainage, you can investigate different varieties, the response of the transpiration. Under drought conditions, you have the scale and the water is coming from the container, and you can measure the transpiration, and you can see the effect of the different irrigation regime or the fertilization regime on the crop. And it's a great research tool. If you want to transfer it to the farmers, that the farmers will use it, it's still under research, and it's not simple that the farmers will use lysimeters. Mainly, we can use it in research institutes, universities, and companies. So lysimeters are great, but they should be designed specifically for any specific case of crop, of soil, of irrigation method. So sprinkler irrigation and drip irrigation are different. You sometimes using flood irrigation, they should be also different. And for different soil, the size and the lower boundary conditions are really important. And you need to think while you're designing, don't just take any container and start your experiment. You need to think and look at the literature before what should be the size, what should be the lower boundary conditions of this lysimeter. After you design, of course, you need to build, you need to operate, you need to calibrate, and you need to maintain the lysimeters. It's a lot of work. And it's a big investment to build. And before you're thinking about lysimeter, you need to think what will be in 3 years, because you need manpower to operate, to build, to calibrate, to maintain. And this is a lot of money. So for the managers here that want to think about a lysimeter, think about the budget, not only for building, but also for the operation, calibration, and maintenance, because you don't want to make a white elephants that it will sit there and do nothing, because it's a huge investment. Also, after some time, you generate a lot of data from the scales, from the sensors, from the models associated with the lysimeter station, and you need to manage the data. You need to analyze the data. you need to store the data and somehow to make this analysis. Otherwise, this container will just grow plants and the data will be gone one day. So it's a shame. So you need to store the data appropriately with the treatments, with the time, and put it in several locations on cloud, etc. Otherwise, all this information will be gone. And it happened, of course, in the past. I think you need multiple users for lysimeters, a group of physiologists, plant scientists, yes, together with soil scientists. It's the optimal way to work with lysimeters. The soil scientists will be interested on processes in the soil. The plant scientists will be interested in processes in the plant, and together they can operate the lysimeters quite successfully and generate a lot of papers and a lot of knowledge, a lot of information that can be used later to have a better world, better food, better quality with lower resources, and also less contamination to groundwater and air. Okay, thank you very much. That was my presentation, and I'm willing to have as many questions as you have.
Can you please brief about your summer course program, and then we can go for the question and answer sessions.
Okay. Okay, summer course program in my institute. This is a last year date. They will slightly change next year. So we have a 1 month course. It's called the Sustainable Agricultural Solutions. And the course is providing the students with cutting edge knowledge and technology related to things that we are experiencing here in our conditions in the desert. We are talking about soil and irrigation and plant other abiotic stresses. And also we are talking a little bit about aquaculture, growing fish and algae here in the desert. So the students are coming here for 1 month. They should be under some degree, bachelor, master, or PhD degree. And in the end of the course, they are smiling. They are interacting with us through this month, and they will go to field trips. They will going into our laboratories. They will do experiments. We will give them presentation. Finally, they will give us presentation about their research, small research that they did here. Yeah, so it's really fun. They will have some tours in Jerusalem and in other locations in Israel. Yeah, there is some tuition for the course. Chinese and Indians may apply for scholarship to the course. And yeah, I can send you the link to this course. And you can see later on, you can see the video that the student prepared a while ago. And of course, you can see this video later. This is very interesting course. And I think that even to come to 1 month to Israel, even if you are not staying more than this, it's nice because you can later on interact with us and see what's going on, cutting edge research that is done in our institute. Some of the students are staying for a master and PhD degree, later on sometimes postdocs, and it's really yeah, methodology. Also in this course, we have some units of methodology. It's not a course, it's not a full course, but we have some explanation about the methodology, usually micrometrology near the plant and not high in the atmosphere. Yes, we are interested in micrometrology.
Thank you, sir. So we can go with the question and answer session. So I request all to post the questions in the chat box so that we can take it one by one. So far we have two. Yeah. Mr. Vijay Kumar, you want to ask?
So I see here one question. What is the ratio, drainage, and amount of water applied in the crop? What is the most suitable irrigation method for lysimeter study? So most of our irrigation, by the way, in Israel is drip irrigation. We have some sprinkler irrigation. About 30% of the irrigated fields are sprinkler irrigated. The rest is drip irrigation. We do not have any flood irrigation. Flood irrigation, basing, or furrow is not done in Israel. Therefore, our lysimeters are designed for drip and sprinkler. The most suitable method is drip irrigation, because then you can locate the drippers within the lysimeters and you are sure that the water is flowing inside. With sprinkler, it's hard to know because some of the water will flow outside and some inside the lysimeter. And yes, you need to arrange the lysimeter in a way that drops will not jump outside later on. So this is the irrigation method. Is drip irrigation is the best, not only for the lysimeters, the best also for the agricultural field, but for the lysimeter, it's very important because then you know that water flow inside the lysimeter. So the ratio of drainage and the amount of water applied is highly dependent on the salinity of the irrigation water. If you have a very good water, you don't need drainage. If you have saline water, if you don't drain and not flush the salt a little bit out from the root zone, you will have accumulation because water are transpired from the plant and the concentration in the root zone is increasing. Therefore, you need to leach, and the leaching fraction is dependent on the salinity of the irrigation water. Usually for medium water, when we have 2-3 decisiemens per meter, 30% of drainage should be enough. If we have higher than this, we require more. If we have lower than this, we almost don't need any drainage. Drainage is not something that we want to have, yes, because with the drainage, we have agrochemicals that are flushed below the root zone, and we want to minimize the drainage.
There's another question. It's like how the drainage water was collected and what was the size of perforations on the bottom side of lysimeter?
Okay, so I will go back to the presentation. Wait. Okay, so there are different ways to collect the drainage. Sometimes we are collecting the drainage in a big container because we want to come there every week to collect the drainage, and then it's done manually with a pump or automatically with a pump. Here in this carousel, we have a 10-liter container in the drainage for collecting the drainage, because we can empty the drainage even twice a day. It's done automatically. Different experiments have different drainage collection. For instance, in this date palm operation, we have one scale for the lysimeter and the plant, and we collected the drainage in another container that was located on a scale. So we have a separate measurement for the drainage, and it will give us also the accumulation of the drainage with time. Here in this container, it's only once per week we have the drainage, yes? So it depends on the research question, what you want to investigate. All in all, the drainage is the important part here, because if you have the drainage and you have the irrigation, you can make the balance and estimate the what the plant is using, and this is highly important.
Thank you, sir. We have another question. What precise technique do you use to contain the evaporation and study transpiration exclusively?
Okay, so to contain the evaporation, so you mean to minimize the evaporation, yes?
Yeah.
So in many farms in Israel, we are using plastic mulch on the surface. This plastic mulch can be transparent, and then they're even using it to increase the temperature in the winter. It's cold in Israel, so you want to have a direct solar radiation inside the soil, and then because you have this greenhouse effect, so it will increase the temperature in the soil, and you can have a benefit from it during winter time. In the summertime, we are using this plastic mulch to disinfect the soil. The temperature can go to 60 degrees, even more, and then obviously plants is not so good for them. But plastic mulch is something that we are using a lot, and we are using on top of the lysimeters. We have this black and white plastic mulch, white on the top and black on the bottom. So it's like a sandwich plastic mulch, and we are using it also in agricultural conditions. The reason for the white is to reflect the radiation. It simply has a higher albedo, and the black is that sometimes you don't want that the radiation will penetrate into the root zone, and then you're minimizing the direct radiation. So this mulch is often used, but you can use any mulch that you want. It can be from stones, it can be from, I saw many mulches that people are using from organic material, etc. Whatever you have there in available. Remember that in the end, you're not canceling evaporation, you're just minimizing evaporation. And also remember that you need place for the plant to grow. Yes, the stem need to come out from the soil. And then you need to make some holder for in the plastic or the whatever mulch that you are using, and from there you will have also evaporation. So it's never canceling this term. You will have yes to minimize this term.
Any other questions? So if there's nobody to ask, like I wanted to know, how was Hydros model different from the Epson?
Please ask again, how this?
How is your Hydros model different from the Epson model?
I didn't understand the second model.
Epson.
Okay, so this model for fertilizer or pesticide?
Yeah, that is also for all water and all other. It includes all other inputs also.
Yeah, I'm not so familiar with the second model that you mentioned. I'm sorry. I can mention a lot about the Hydros model. It's a very powerful tool to estimate water flow and solute transport, also heat transport. Today we are dealing there with many different contaminants, also PFAS and viruses, and many emerging contaminants, heavy metals, etc. So this is really powerful in the chemistry. The plant part in Hydros is not highly developed, but we are working on it. So all the time 2 years ago, we published a paper about root distribution and how this roots is characterized and how stress will influence the root distribution. So it's a module that we just inserted into Hydrous. Recently, one of my colleagues developed a module that are uptaking nutrients into the plant and distribute the nutrients into different parts of the plant. So it's not only a soil model, it's also a plant model. Still, it's not perfect, and there is some place for improvement, but in terms of dimension, it can be one-dimensional, it can be two-dimensional for drip irrigation studies, or it can even be three-dimensional, but then you need a really powerful computer to simulate the conditions. So yes, Hydrous is developed. There are more than 300 papers each year that are using Hydrous simulations, and this model is growing. Yeah.
And is it necessary to have a load cell for each lysimeter? For example, we have lysimeter facility, which is like a 2-meter long tube with almost 30 centimeter diameter. We grow sorghum and millets because the root growth is around 2 meters. So we
Yeah.
do have a bottom plate, and our water is not saline, so we don't estimate really the drainage. But to limit the evaporation, we use these PVC beads on top of the tube of the soil, so to minimize evaporation. So we
Sure.
don't have really, since they are placed in a trench, so we don't really have individual load cell. So we have a pulley system where we lift each of the tube every time and measure the weight. So that's kind of laborious as compared to your lysimeter, since it's not completely automated, but that's the existing facility we have. So
you already answered, yes. So of course, obviously, like in this cassava experiment, we had 160 containers. And 160 containers to put 160 load cells, it's a lot of effort and a lot of money. So we had several load cells that the students came and they put the cassava on a scale on bi-weekly, and they measure the mass, not the weight, the mass of the entire thing. And yes, it's a lot of work. It's laborious. Yeah. In this carousel, each individual has a load cell, have 24. In this pomegranate experiment, I had a mixed. I had 80 containers, 40 of them were on load cells, 40 of them were not on load cells. Yes, so the plant doesn't know that if it's on load cell or not, just we have more or less work to do. And yeah. In the end, labor costs money also. I think this is the most expensive part of the research is labor. Yeah, and if you can save it, it's fine. And also labor, people are doing mistakes. And machines, if you train them correctly, they do less mistakes. So you have more accurate results. People will not come during the holidays to measure. And during nighttime, it's very hard to bring people. So we are limited with people. It's not only laborious, it's also limited information. And many processes, for instance, happening during nighttime, and we want to know what's going on. So scales can help us for this. Or early in the morning. I don't know if you want to come to the field very, very early in the morning.
You have done experiment in sweet sorghum.
Yes, this experiment was salinity and sweet sorghum. Yes.
Okay. What is the optimum water requirement for sweet sorghum?
Yeah, it's a challenging question because the experiment is done in a greenhouse. You see, it's obviously not similar to the outside. And then the plant is growing from a seed in the beginning until mature plant. So in different time during the experiment, it has different transpiration. And different salinity had different transpiration. So the water requirement can go from 0 in the beginning to 7 millimeters or 7 liters per meter square in the end of the season in these conditions that we had. Yeah, so it can be different because of the climatic conditions, because of the salinity, and because of the size, the phenological stage of the plant. So I cannot give you 7.5. Yes, it's changing from 0 to 7 in our condition. Maybe in your condition it's different. You need to test it on site.
The ultimate aim for seed sorghum production is juice, right? So is there any relationship between uptake of water and juice yield?
Of course, the juice yield, the concentration of sugar inside, it was different. Also with salinity, yeah. Also the yield itself, the seeds yield was different. Yeah. But during this experiment, when you're doing 5-6 different treatments and you're growing the plant and you actually put a monitor on the plant. Yes, think about a person that sitting on a bed and you put all the sensor on top of his body and you see the heartbeats. You can see a lot from it. Yes, if the person is okay or not okay, if he's happy or not. Like Apple Watch today, we have this Apple Watch and it will tell you, okay, you are sitting too much time now, you need to practice. So this is the similar information that you get from the lysimeter. It's telling you what's going on with the plant, how the plant behave now.
Thank you, sir. So if not for any further questions, I think we can wind up the session. I understand this may be a little complicated for people who really haven't worked with lysimeters yet. But as Mr. Naftali mentioned, Dr. Naftali mentioned, it's really a powerful tool to conduct drought experiments and understand the water relations in the plants. So, Ilangovan sir, should I convey or it's like...
Go ahead. Before that, I would like to, before the formal vote of thanks by Srividya, I would like to thank Naftali on behalf of our director, Indian Institute of Millet Research, having given opportunity to deliver a lecture. And for anything, if it is food or water, but optimum is required. We cannot take it excess, we cannot take it low also. So optimum is always required. So you nicely narrated with many crop experiments, and thank you so much. And I request Dr. Srividya to propose vote of thanks.
So thank you, Dr. Naftali Lazarowicz, for such a detailed presentation on lysimeter. So we'll be keeping in touch with you for many other experiments and calibrations which we are conducting here. And I would also request all the participants to take help as he is the expert in this field. And we also thank all the participants. We had close to 50 participants today. And from our institute as well as from our ICR sister institutions, like from IIOR, Indian Institute of Soil Science Research, and IIFSR, Central Salinity and Water Research Institute, NRRI Cuttack, and Institute of Pulse Research, and many other institutions. So on behalf of all, I thank you, sir, for this wonderful lecture. So thank you.
Thank you very much for inviting me.